So now we have Kerry Emanuel, who's a colleague of mine, a professor in Earth and Planetary Sciences. And he's interested in moist dynamics, tropical meteorology, a great expert on hurricanes. He's co-director of the Lorentz Center and was also very close to Charney and Lorenz and was one of Charney's last students.
Thank you very much and good morning. Before I begin my remarks on Ed Lorenz, I can't resist adding a little vignette to what you just heard about Charney. I was also a student of Charney's and really loved interacting with him. We did like to argue with each other a lot in a very productive and friendly way, sometimes very vigorous, and I'll tell you one such argument we had in his office when I had been arguing with him about a finer point of something called the Howard semicircle theorem, which is quite a well-known theorem in fluid dynamics. And we went back and forth, and it got a little bit heated, and finally Charney said, "All right," and he picked up the phone, and the next thing I heard him say is, "Lou, I've got this kid in here, Emanuel, would you talk to him about such and such?" He put me on the phone with him, and there came a very polite barrage over the phone, and I clearly lost that argument. And Jule was very magnanimous. He never smirked or looked at me. We just never discussed the subject again. He was great that way. What I'd like to do with you this morning is to tell you a little bit about the life of Ed Lorenz and interweave that with his scientific accomplishments. I'm going to go a little bit back and forth between those two. Many in this room will have remembered Ed very well as a beloved colleague, mentor, and teacher. And he was, of course, the author of one of the greatest intellectual advances of our time. It's particularly wonderful, by the way, that today we also have all of Ed's children with us. And I hope I can do a little bit of justice to the life and legacy of their father. Ed was born in West Hartford, Connecticut in 1917 to Edward Henry and Grace Norton Lorenz. And one of the reasons I mention this is they both had connections to MIT already. Edward Henry majored in mechanical engineering here. And although he was, like his son, small in stature, he held at the time the MIT record for the 2-mile run. Grace's father had developed the very first course in chemical engineering here at MIT within the chemistry department. That was back in 1888. And her mother founded the Department of Home Economics at the University of Chicago, the institution from which Grace ultimately graduated. Ed always attributed his love of games, which you heard a little bit if you were at the dinner last night, particularly chess, to his mother Grace's influence. Ed's parents met at Waterville Valley, a summer resort in New Hampshire, and after they were married in 1916, continued to summer there, imparting to their son a deep and abiding love of the outdoors. Ed's fascination with numbers was apparent at a very early age. And not long after he learned how to multiply, he taught himself all the perfect squares up to 10,000. He had a really great ear for music, and by the time he was 3, he could already tell that his mother was singing off key. His passion continued to develop, and many of you will remember attending concerts with him and his wife Jane at Chautauqua Resort in Boulder, where they often spent part of the summer, or at MIT, where they were both avid patrons of the Student Symphony Orchestra. Well, like his father, Ed was small in stature, and he didn't excel in team sports, but he could swim underwater farther than any of his peers, and owing to his light weight, he could reach mountaintops faster than most. He later related that mountains and music were his greatest spare time interests. Curiously enough, Ed was only 7 undergraduates entering Dartmouth in the year 1934 who would major in mathematics. In 1938, he entered Harvard's graduate school, and he worked on a problem in mathematical physics under the guidance of George Birkhoff. Ed relates that during his graduate years, he seldom saw any number other than 0, 1, and 2. Such was the nature of the math he was engaged in. In 1942, just months before he expected to receive his doctorate, though, the war intervened, and he chose to become part of a team of weather forecasters for the Army rather than to be drafted. He enrolled as a cadet in the Army Air Corps in a special eight-month master's program at MIT to train as a weather forecaster. While the forecaster training was rigorous, MIT's illustrious faculty, which included the likes of Herb Willett, Henry Houghton, and Bernard Horowitz, couldn't resist teaching their students some theory. But Ed had trouble understanding the connection. In Ed's words, not only were we never shown how to use the dynamical equations to make weather forecasts, which I had naively assumed was the reason for our studying dynamic meteorology, but we were not even told whether they could be used in this manner. I also learned that there were outstanding meteorologists at other universities who believed that it was impossible. And I think it's very important for particularly the younger people here to understand that in those times, it was not accepted very universally at all. I should say it wasn't accepted at all by people in the field that you could actually do this kind of deterministic forecasting. So the dichotomy between the theory of weather and the practice of weather forecasting fascinated Ed throughout his career. In the summer of 1944, Ed was sent to Hawaii, where he absorbed another 2 months of training in tropical meteorology, and then he flew to Saipan in October. There he helped to set up weather forecasting operations in support of airborne bombing raids. These forecasts relied heavily on observations made in previous raids, but Ed complained that the pilots, to save time, would often simply repeat the forecast as the observation. This made for really good forecast verification, but hardly helped the forecasters make the next forecast. In the spring of '45, the weather operation was transferred to Guam, and Ed was made head of the upper air section. And some insight into Ed's character during this period is provided by one of his fellow forecasters from back then, Patrick Supis. And Patrick says that although Ed was not a strongly outgoing individual, it turned out he rather liked conversation on many topics. And of course, as those who knew Ed will find unsurprising, he knew a lot and was prepared to talk about a great many different subjects. Those who know Ed principally through his research contributions might easily overlook his interest in the practical art of weather forecasting and his love of weather in general. But generations of students and colleagues here at MIT will remember many occasions when Ed would appear silently in their office as if by magic and enthuse over some feature of the current weather map. After the war, with much deliberation, actually, Ed decided to formally switch from mathematics to meteorology. In his own words, mathematicians seem to have no difficulty in creating new concepts faster than the old ones become well understood. And there will undoubtedly always be many challenging problems to solve. Nevertheless, I believe that some of the unsolved meteorological problems were more fundamental, and I felt confident that I could contribute to some of their solutions. Ed received his doctorate under Jim Austin in 1948, and shortly thereafter married Jane Lobin, who had been working as a research assistant in the meteorology department at MIT. Jane was born in Dayton, Ohio in 1919, but spent most of her childhood in Cedar Falls, Iowa. Her consuming interest was flying, and she flew small airplanes before she was old enough to drive a car. And you will remember some of the problems that Ed later had with Jane's piloting abilities, being treated to terrifying flights around New Zealand and so forth, but she was a good pilot. Her interest in flying led naturally to studies in meteorology, which in turn led her to an appointment at MIT. Following their marriage, they settled in Cambridge and lived in the Boston area for the remainder of their lives. Their 3 children shared Ed's love of game and the outdoors. According to Ed, many of my winter weekends were spent taking all of them, one of them or all of them, usually with my wife as well, to some ski area north of Boston. This, of course, was just what I'd hoped would happen. Ed's devotion to his family was evident to everyone who came to know him well. Ed accepted a job as a research scientist on a project to study the general circulation of the atmosphere, headed by Victor Starr, who had come to MIT from the University of Chicago the year before. Starr became Ed's mentor and close friend and was, next to his parents, the most important influence on his intellectual development. One of the most important events during this period, and Joe Podolsky alluded to this in his talk, was a visit to Jule, Charney, Norm Phillips, and others working under the direction of John von Neumann at the Institute for Advanced Study in Princeton to apply the newly developed digital computer to the problem of numerical weather prediction. At this point, Ed and Victor were not convinced that numerical solution of the equations governing atmospheric flow was even possible. Although Ed was not entirely persuaded during this visit, by the mid-1950s, he saw that this was the way of the future. Ed must have made a positive impression of Charney because, as you just heard a few years later, Charney made his own acceptance of the offer of a faculty position at MIT contingent upon the promotion of Ed. It was during this period of the early 1950s that Ed made his first lasting contribution to meteorology. Victor Starr had speculated that some fraction of the potential energy of the atmosphere could be converted to kinetic energy, and this fraction became known as the available potential energy. Ed took some time to work out the physics and math of it. In his words, it finally occurred to me around 1953, I think it was. Actually, it was one night when I couldn't sleep. I was turning these things over in my head, and it suddenly occurred to me, why not define available potential energy as just the excess over the minimum that you could get by redistributing the mass adiabatically? And this led to his first and very highly influential paper published in 1955 on available potential energy. Now, I'd like to do, because it's impossible to cover everything, but I want to skip directly now to the origins and evolution of the discovery that changed the world in many ways and made the name Lorenz known to many. And here I'd like to gratefully acknowledge the help of my colleague Dan Rothman in getting the facts straight of this rather fascinating story. I'd like to just begin by putting this whole development of chaos theory in the longer history of the concept of determinism, because I think it's very hard for us in 2018 to imagine how people viewed the material world before the Renaissance. Causality was a theological question, and the word science had not even been invented yet. And as you know, the great thinkers of the Renaissance, like Galileo, Copernicus, Kepler, and ultimately Newton, changed all that, so much so that by 1814, Pierre-Simon Laplace could write in his philosophical essay on probabilities that an intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed, if this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. This very bold statement of universal determinism marked the dawn of an age of astounding scientific discovery and technological progress. Determinism reigned for about 150 years, and it was not even much perturbed by Henri Poincaré's 1903 deduction stemming from his work on the three-body orbital problem, that certain dynamical systems could be practically unpredictable owing to their sensitive dependence on initial conditions. A more serious challenge arose in the mid-1920s in the form of Heisenberg's uncertainty principle, which asserted that the product of a particle's position and velocity cannot be known to better than a definite finite accuracy. Yet many physicists believe that this had little implication for the behavior of the macroscopic world. Now, it's very important to note here that Ed never intentionally entered this fray of determinism. He had a very different battle to fight, and I think it's important that we realize what that battle was. By the middle of the 1950s, there was a dispute among meteorologists about whether numerical weather prediction could ever, even theoretically, outperform purely statistical forecasts based on linear regression. You see, at that time, if there was a science of weather forecasting that was actually being applied, it was statistical forecasting. And I remember, some of you may remember, taking a course in statistical weather forecasting from Ed Lorenz here at MIT in the 70s. But Ed felt that the advocates of statistical forecasting had misinterpreted a theorem by his MIT chess partner, the mathematician Norbert Wiener, that seemed to suggest that, in principle, statistical forecasts could perform at least as well as integrating equations in any deterministic system. Now, we think that's a really kind of a crazy idea now, but the reason we think it's a crazy idea is really because of Ed's work, ultimately. Ed just felt that it had to be wrong, and he set out to prove it. At a meeting in Madison, Wisconsin in 1956, he told an assembled group of statistical forecasters that he proposed to test their hypothesis, that is, the hypothesis that you could always outperform or at least reproduce a deterministic forecast statistically. He said he was going to test that by integrating a set of nonlinear equations on a computer, deducing a set of optimum linear prediction equations using standard methods, and finding out whether they could actually reproduce the numerical solution. He knew that to do this, he had to find a set of solutions or equations that did not repeat themselves. That is, he set out to find some deterministic system that was not ultimately periodic. And he wanted these equations ideally to be relatively simple. But he also needed a computer to integrate them. Now, in those days, computers were just in their infancy. They were largely confined to big computing centers. But at this point, he had been made a faculty member here at MIT, filling a position vacated by Tom Malone. And one day, a postdoctoral fellow by the name of Bob White, who later became the head of the Weather Bureau, suggested that Ed purchase a computer of his own. Now, this concept back then was unheard of, but they set about shopping around for something for months, and they settled on the Royal McBee LGP 30. And I think we had an issue of one of those yesterday up in the Green Building. It was noisy, and it filled his office, but it could perform 60 floating point operations per second, or flops, a huge improvement over mechanical calculators, and could store, get this, 4 kilobytes of data. Your smartphone performs at about 5 billion flops and may have 64 gigabytes of storage. By 1959, Ed had settled on a set of 12 equations representing a highly reduced model of the global atmosphere, and had found for certain combinations of parameters solutions that seem never to repeat. Here is a description of his 12, sort of in compact notation, his 12 equation system. It's a nonlinear system. And the solutions he did ultimately find by trying many different combinations of parameters, a solution. This is taken directly from a conference report he submitted to a conference in Tokyo that took place in 1960. He did ultimately find a solution that didn't repeat itself. Okay, that was what he was after. He'd proven what he said. Well, then he applied these optimal set of statistical equations, and lo and behold, they, only after a short time, they diverged from this, and he could not reproduce the solution with statistical equations, so he actually proved what he set out to prove. Now, during the period when he was performing these calculations, there came the much celebrated moment when he restarted one of the calculations by re-entering the values of the 12 variables at a particular time step. He stepped out, and this is according to him, for a cup of coffee, and on returning, noticed that the output didn't resemble that of the original simulation. He suspected that this complicated machine with lots of vacuum tubes, that one of the vacuum tubes had failed. That turned out not to be the case, and came to realize that it was the rounding he had done, which we heard about yesterday, when he re-entered the numbers that caused a small perturbation that grew. And it ultimately grew to the point where the difference was as large as the difference between any two random realizations. I think it's telling that in the body of his 1960 Tokyo conference report, he didn't mention this incident. He was focused on the non-periodicity of the solution and the inability of the statistical equations to simulate it. As was traditional in those days with papers, the paper itself, the printed paper, concluded with a summary of the discussion that took place at the meeting following its presentation. Bert Boleyn had asked Ed, did you change the initial condition just slightly and see how much different results were in the forecasting this way? Ed related that they had tried that, with the result that the perturbed solution diverged from the control exponentially in time. After the conference, Ed turned his full attention to the predictability problem. He now wanted to understand the relationship between aperiodicity and loss of predictability. And he felt he needed to work with a much simpler system to get at this problem, and worked hard at first to simplify the set of 12 equations, but he failed at doing that. And much later in his career, he showed that, in fact, it was impossible to simplify this particular set of equations. So Ed's search for a simpler system bore fruit actually when he visited Barry Saltzman in 1961. Saltzman showed him a set of 7 equations that represented convective flows. Those 12 equations were a reduced model, by the way, of the general circulation of the atmosphere. Barry was interested in the periodic solutions, but he did show Ed one solution that refused to settle down. In this solution, 4 of the 7 variables decayed towards 0, and Ed realized that the chaotic solution could be represented by equations dealing with only 3 variables. And so with Saltzman's blessing, he published this 3-equation set in 1963, and these are now known as the Lorenz equations. The variables could be plotted in a 3-dimensional perspective or in 2D sections, and the nature of the strange attractor could be revealed in all its glory. Ed showed that this peculiar and beautiful fractal geometry of the attractor was intimately tied to sensitive dependence on initial conditions, and some consider this recognition to be Ed's greatest achievement. So here's a slide showing the Lorenz equations and the values that he took in the published paper. And if you happen to have an iPhone, you can get an app called My Attractor, and you can integrate those equations in less than a second and display them on your phone, and it's actually quite fun to do this, so I recommend it. It just shows you how far we've come. And as you are probably aware, the interesting thing about the solution of these equations is that they essentially never repeat themselves, and they occupy this very fascinating and, I think, beautiful fractal geometry. Now, the 1963 paper is interesting for a variety of reasons. Here's just a Xerox, if you will, or a copy of its title page. Very simple, beautiful, short title, beautiful, short abstract. Not abstracts that fill pages. And it's kind of interesting that for the next 10 years, a little bit more, 1963 to 1974, this paper was cited 3 times by people outside of meteorology. That's all. It just took a long time for it to filter out. When I was here as a student in the early 70s, the first time I heard of it is a course in dynamics I took from Ed Lorenz. And I was really shocked that I hadn't heard of this before. I thought this was some failure of my education, and I started asking people who were majoring in physics if they'd heard of it, and I ultimately discovered that it was just simply not very widely known, except in mathematics. It was beginning to be known by then. and meteorology, of course. So finally, around 74, Ed's work was brought to widespread notice in the mathematics community by James York, Alan Fowler, and Stephen Smale. The topological properties of Ed's strange attractor were of special interest, and the explosion of research in chaos theory ensued. But by then, Ed had discovered something arguably more profound than his earlier work on non-periodic systems. As illuminating and exciting as his 1963 paper was, it posed no real threat to the basic idea of determinism because the predictability horizon, that is the amount of time you could go forward before you lost any resemblance to the true solution, the basic predictability horizon of the 63 system increases without limit as the initial condition error becomes vanishingly small. But in 1969, he presented a system of equations representing flow with many different interacting scales. The key feature of such systems is that the amplification time scale gets shorter sufficiently rapidly with the spatial scale of the disturbance. In Ed's own words, it's proposed that certain formally deterministic fluid systems which possess many scales of motion are observationally indistinguishable from indeterministic systems. Specifically, that two states of the system differing initially by a small observational error will evolve into two states differing as greatly as randomly chosen states of the system within a finite time interval. Within a finite time interval which cannot be lengthened by reducing the amplitude of the initial error. That is, the predictability time horizon approaches a finite number as the initial condition error becomes arbitrarily small. It's a singular limit of the system. If nothing else, quantum uncertainty prevents the initial error from actually becoming zero. So this is, I think, the really profound result of that 1969 paper expressed graphically. So on the bottom axis, we have the size of the initial perturbation that you're going to add to the system. And on the vertical axis, the predictability time horizon. For certain kinds of chaotic systems, like the 1963 system, as you reduce the initial error to zero, the predictability time horizon recedes without limit. But for the 1969 system, it doesn't. Even as you approach the limit that the initial condition error is zero, the predictability time horizon remains finite. That is, these systems are formally indistinguishable from systems that can't be predicted. Now, no one has yet succeeded in proving that this is true of the actual Navier-Stokes equations, but most of us suspect that it is. So history may well record that Ed Lorenz had hammered the last nail into the coffin of Cartesian universe. Ed himself wasn't immune to some of the philosophical implications of his work. And in his book, The Essence of Chaos, mused in characteristic Lorenzian fashion on the problem of free will. This is what he said. I love this. We must wholeheartedly believe in free will. If free will is a reality, we'll have made the correct choice. If it is not, we shall not have made an incorrect choice because we shall not have made any choice at all not having the free will to do it. Those of us privileged to have known Ed Lorenz will remember him as a gentle, quiet soul, almost painfully shy and modest to a fault. But if you engaged him on a favorite topic, a fine point in atmospheric or dynamical systems theory, the virtues of a particular mountain trail, or anything to do with his extended family, with a twinkle of his bright blue eyes, he would come to life. And at such times, one always felt as if he were inwardly smiling at life. Ed was a true gentleman, and in his own quiet way showed a deep affection for his wife, Jane, and their children, and an old-fashioned sense of chivalry toward Jane. We all miss him. Thank you.
Thanks a lot, Kerry. Do we have any questions for Kerry? back. Please come down to the microphone.
Hi, Kerry. Thank you very much. That was so interesting and filled in some things I don't recall, but I'm glad to know. I was thinking, as you mentioned, you sort of alluded a little bit to the development of turbulence. You didn't mention it exactly, but I would like to ask you, do you know what interaction Ed had with people developing the turbulence theory? I'm thinking, I don't know if he interacted directly with Obukhov or Kolmogorov or Monin or any of them, but there was a theory making somewhat related discoveries more or less in the same decades, and I'd like to hear your comments about that.
There were, and I don't know specifically of interactions he might have had with the people you mentioned here at MIT. Does anybody else know the answer to that question? I didn't come across any description of such interactions. Doesn't mean they didn't take place. I think Joe Podolsky had.
Joe?
Is there a straightforward explanation of what was different between the 69 and the 63 models that led to this remarkable change?
I guess it all hinges, Joe, on one's interpretation of the word straightforward. In my mind, it is the interaction, continuous interaction among scales, and the fact that in that system, as you went to smaller and smaller spatial scales, the sort of exponential, the e-folding time of disturbances got faster. It depends on the shape of the spectrum of the turbulence, and if that's true, if that slope is sufficiently shallow or sufficiently steep, then the fact that the smallest disturbances grow very fast and interact ultimately with the larger disturbances is the source of the loss of predictability.
Tim Palmer.
Kerry, you mentioned the fact that before the war, Ed had done a master's degree in mathematics under Birkhoff. And Birkhoff was some sense, the natural successor of Poincaré that you mentioned about the three-body problem. And clearly the leading figure in the theory of nonlinear dynamical systems at that time. Is there any evidence that any of that rubbed off on Ed, either consciously or subconsciously, and influenced then his work in the 60s, 50s and 60s?
That's a really interesting question, Tim. The only way I can illuminate it, and it's probably not much of an illumination, is that in The Essence of Chaos, Ed relates that at the time he was developing the 1960, the 12 equation set, and the Berry-Saltzman set in 63, he says he was unaware of the three-body problem work. And I think that's curious because his advisor had worked on that problem. I just don't know how to resolve that. But, yeah.
Bruno?
Hi, we are all friends, so let me correct you on a piece of history. Before Copernicus, Nicolas von Cusse is called in French Nicolas de Q. He was a German theologian, he was a cardinal and so on. He introduced the idea, of course, that the Earth was not at the center of the universe. There could be many universes. He was not a deterministic person. And people tend to forget about him. Then, okay, this piece of history. Then coming back to a shorter time, when I arrived at Princeton, von Neumann was dead already, and Jule Charney was already at MIT. But do you know anything about von Neumann's understanding of chaos? For he was a rather deterministic person, your language.
You're asking about Charney's knowledge of.
Which,
I don't know about that.
You don't know.
I think what my guess is that what he learned about it, he learned directly from Ed, but I don't know for a fact.
Okay, thank you.
Last question before coffee break.
Yeah, regarding this interesting question about whether anything from Birkhoff on dynamical systems rubbed off on Ed, it had always fascinated me that in the early 60s papers on strange attractors by Ed, he essentially uses the concept of the Poincaré return map to analyze what that thing is doing, but I don't think he used the term Poincaré map. So I don't actually know whether he just independently reinvented this as he just out of pure thought, which he could well have done, or whether something had sat there subconsciously and came back when he really needed it. But it is essentially the same technique that had been used in analyzing three-body problems in dynamical systems.
Ed has an interesting comment about this, Ray, in his book, where he says one of the things that got him excited about the Saltzman equations, the 63 work, was that he could finally apply this form of mapping. I don't recall whether he actually used the term Poincaré, but he knew about that mapping, or he says he knew about it.
Yeah, in fact, he gave a seminar to the applied mathematicians in 63 or 64 at MIT, and he was fully prepared to talk about the work on chaos using those concepts and using that terminology.
Thank you very much, everybody. So we're now going to have coffee break up the stairs and off to the left, and we'll be back here at 11.